Hi everyone and welcome back to the multiverse of 100 plus data science project series. In this video, we're going to be creating here an carotid segmentation projects using UNET architecture. So without wasting time, let us start our tutorial right now. In order to building here the carotid segmentations projects using UNET, we're going to be using here a dataset from Kaggle that's called Carotid Ultrasound Images. So this is the dataset. So if I go down, you can see in the data explorer sections, you can see the datasets called Common Carotid Artery Ultrasound Images. We have the two directory inside that. One is expert max images, the max images, and another one is the real images. So it also having one data.csv. So you can directly download the dataset from here, or otherwise you can also access it using Kaggle Hub library in Google Colab. So how can you access them? Just you need to go on here, just need to copy here this link. Up to that, the user's name, Kaggle user ID, as well as the name of the projects or the datasets, carotid ultrasound images. So you're going to copy this out and we can easily access it using Kaggle Hub library. So I am not going to do the live coding. I am just going to explaining all of the code line by line. So see how can you download it and how can you access the dataset from the Kaggles. So we're going to using here a module called Kaggle Hub. And inside that, you're going to paste here the link that you copied. Link not actually, it's nothing but the name, the Kaggle user ID name, as well as the dataset name. So carotid ultrasound images that you can see, I pass it out here. Also, one more thing, make sure your runtime in the form of GPU. You can see T4 GPU. Make sure you select it and click on cancels. And then I'm simply going to click here. I can click here. Otherwise, I can also using here the shift enter. So when you press the shift enter from your keyboard, it will running these shells. So what it actually do, it will directly getting this data set from the Kaggle website. So it is just taking few minutes in order to downloading this one. But if you are doing it in the local, you can also do it. But obviously it will taking time. And then we install here the Kaggles, because you need to also install the Kaggles in order to access the datasets. See, we download the dataset from here in our Kaggles using the Kaggle Hub library. And after that, you install here the Kaggles and also creating here a folder called Kaggles. And inside there, I have to give it here on kaggle.json file. So what is this kaggle.json file actually? So kaggle.json file is containing here the API tokens. So how can you access them? If I go inside that, and if I go inside my profile, and I having my your profile, or you can go to the settings, you can see the API key. You can say create new token. So I can click on create new token, and if I click on confirm or continue, it will creating here a token. Now I can simply go into save it. Okay, this is kaggle.json file. So let's save it on here, and you can see it's saved. Now what I can do is simply going to actually running these shells, but you need to also uploading here our kaggle.json file inside this here. So click on upload, and then I'm going to selecting here this kaggle.json. I'm going to click on open, and you can see I get some kind of warning because find the runtime file should be deleted because it will store for the once a time. Then you create here, we actually give it here csmod. You need to extract it, and then it will try to creating here a directory as well as the tokens. Okay, the expired tokens. So simply I'm going to using here shift enter. So don't worry about this code. You can get this code in the video description of the GitHub link as well, or you can also get here this Google Colab link as well. So you can see requirement already satisfied. That means it's already installed, and it will creating here a directory called Kaggles. I think it's created or not. Okay, it's created internally, and then you can see a kaggle.json and csmod 600 kaggle.json. This one. Okay, we have our tokens. Okay, now we can easily using his Kaggles that you install. That you creating here inside that. So Kaggles datasets, you can using here download, and then you're going to give it here the user ID and the dataset name that you copied. So I'm simply going to using here shift enter. Then it will try to download the datasets that you can see. It's already downloaded. I hope so. You can see you can using here this method, as well as you can also using here these methods. And after downloading this dataset, you need to also starting word, because when you're downloading this dataset from the Kaggle, it will give you 1G file. If I refresh this one, you can see here 1G file. Just need to copy here this path. You can see I just give it to the copy the path, and using here this exclamatory sign of unzip, because I need to also unzip here the G file, and shift enter. That's it. You can see it will directly unzipping all of the files. So obviously taking few time because it is unzipping all of the files from here. Okay, it's completed, that you can see. Now the main important part here. So first what you can do, you're going to importing here some of the important module. So first you import here the numpy as np for doing some matrix multiplications, and import pandas as pd so that you can do the data manipulations or data visualization as well, and import os so that you can also look into operations in like file creations or file handling like that. And you also import here the matplotlib.pyplot as plt in order to do the visualizations. I also import here the random so that you can also generate some random numbers using import cb2 because it's needed at all. It's the computer vision library. Using cb2 we can access the images or you can also read the images. And also import here the TensorFlow. It's nothing but a framework, the machine learning framework or deep learning framework you can tell. And then from TensorFlow.keras.models, we actually use here the models. So you import here the models. Using this model, we can creating here one deep learning or neural network model. And then from TensorFlow.keras.layer, we import here the input, the con 2D, the maxploin 2D, upsampling 2D, and concatenate. So why this upsampling 2D and the concatenate? Because in order to do the segmentations, we're going to using here the UNET architectures. If you don't know what is the UNET architecture, you can just go on my channels and you can follow the link how can you code one UNET architecture from scratch using PyTorch. So in case of UNET, you're also using here the upsampling 2D or you can also using here the con 2D transports. So in this case, I'm going to using here this upsampling 2D. So concatenate is needed because you have one two path, one downsampling path, one is upsampling path in our UNET architectures. Okay, so then from TensorFlow.keras.preprocessing.image, you import here the load image and image to array. Because when you do the predictions or when you load the images in case of TensorFlow, so we need to also convert this image into some kind of NumPy array or array. Then you also import here the train test split is needed at all because in case of machine learning or deep learning, we need to divide our dataset into training and testing. Then you also import here some of the callbacks. Let's say from TensorFlow.keras.callbacks, we import here the early stopping and the reduce LRO plateau. So this is help us to reduce the learning rate based on your actions. Okay. Then we give it here on base path. So the base path is nothing but here. So you can see that's our base path. We having our folder, command carotid artery ultrasound. So I need to refresh it because it just actually unzipped. So you can see it having one same folder, two things. So you need to copy here this from here, and then I can directly pass it down here. That you can see command artery ultrasound and command artery ultrasound images. Then in our base path, we have two folders. One is expert marks images. Another one is US image. This is nothing but the real images. So you add it here, base part.use images and base part.expert marks images. Which one is nothing but my image directory, and this is the marks directory. So I can simply go into shift enter, simple as it is. Now we can see some kind of see, okay, name OS is not defined because you're not running this one, the first one. So that's why this kind of errors. So make sure you're running the first cell and after that go to the next ones. So you can see the some kind of sample ultrasound images that you can see. You can see the slice 250.png, as well as you can see the marks images respect to here these real images. You can also see the length of the total images. So you can see 1100. This is the total number of images and total number of marks as well. Now we can creating here one image files and the marks files. See, we already creating here the variable for directories, and now you're going to creating here a variable for image files. So you can also show it in kind of data frame, as well as you can also do the train test and splitting to our data sets because you're dividing them into training and testing period. Okay. So you can see it's a shortcut. So we're actually using here shortcut, and then we actually using here os.path.join, and we give it here the image directory that we have. You can see image directory, and we also give it here f. So the f is nothing but coming from here. So f.os.listed of the image directory. So what it actually do, it will simply going to creating here an list of the directories and try to getting here all of the images from here, all of the images from this directory, and simply going to using here os.path.joins. Okay, see, it will creating here a list of images inside our directory, the image directory, and then it will passing to inside this os.path.join, and it will sorted them. So how many images file we have and how many marks file we have. So it nothing but give you the file name. See, shift enter, and now you're going to creating here a data frame of the image files, image file and the marks file. Then you can see. Okay, so now you can also going to see this out. So I hope so you can seeing this out like now. So you can give it here one code. So let's say df dot head. You can also see like that. So you can see here you have the image path. So you can see going through this content and covered carotid artery sound as well as the mux path. So you can see it just getting here and data frame. And after that, you can also see the shape, the how many columns it have, or if they're any duplicated or not. So diagram shape, so the shape is look like that, and index is image path and the max path, and it don't have any duplicated value. It also don't have any not null value. As well as we can see the informations regarding our data sets. So you can see the database is nothing but the objects and the objects. Obviously, it should be object because it's an distinct types of data. Now, after that, what I can do is simply going to try to plotting some of the images. So how can you do that? So you can using here this image file and the marks files because you already have the image directory and the marks directory. So creating here two variables for that, for the image files and the marks files. Okay, but you already do it. I hope so. Image file and the marks file, you don't need to do it. But this one is nothing but for creating here the data frame, and this one is nothing but for checking here the file names. Okay. Now, first we are going to give it here as one assertions for checking here is there any mismatch file or not. So let's say in our images directory or in our data set, we having one file which one is and add dot let's say ppng. Okay, ppng. So which one is not an image formats? So you need to first checking that the format is correct or not. Is there any wrong kind of file is available inside our directory or inside our dataset or not. So that's why I just give it here some kind of assertion errors. So assert all I am split and with the dot, I mean the last one, and same thing for the dot for I am aki the zip image file and the mux file, and it say if it have the any problem inside that, just you give it here the mismatch file. So this is nothing but for checking that in the image files and the mux file should be the same. That's mean with one corresponding image, with one corresponding image also having one corresponding marks. So it is taking this one im dot split because it taking here actually taking here all the file from the image file and the marks file as the im variable and the mkey variables. So and it checking here this one is splitting here the first one character, because if you have the if you don't have any the file format, obviously it will give you some kind of mismatch file errors. So checking here the image file as well as the marks file. That's mean with the corresponding image it having the on corresponding marks. So that's why you're having these images. You can see 110 and 110, the same image file and the marks file. So you're checking this on, then you're going to creating here a subplot so that you can also show here images which corresponding to the marks file. Then we are going to importing here. I mean, we are going to actually creating here the 5 images for that. So you're going to using here the random to generate some of the random images file name so that you can also randomly choose the images from the directory. So random image index is equal to random.radiant. We give it a 0 to length of the image file. So from the length of the image file -1, it will try to creating here one name or one index name, and you can simply going to take it from the image file, right? The random number, random images. So you have the image path. So os.path.join, we give it here the image directory, and from this image file we give it here the random index. So based on this random index, it will try to getting here on random number of image and random number of marks. Same thing for marks path. Now we have one random image path and random marks path. Now we can simply going to convert them into BGR to RGB, because see OpenCV read the image in the form of BGR, blue, green and red. So to convert them into RGB images, so you can see cb2.cbt color, we directly give it here cb2.imread. You can also creating here a separate variable for that, cb2.imread, and you give it here the image path and cb2.color bgr to RGB. Simple. Same thing for marks, because marks is nothing but one grayscale types of images. If you can see the images, then I can show you. Just go on here and export marks. I think I can also visible these images. So let's see. Yeah, you can see the marks. So marks is nothing but one grayscale images that you can see. Okay. So the close tab. Yeah. Okay, fine. And then you can see we can simply go into read it marks path and cb2 dot grayscale. Okay, cb2 dot grayscales. And after that, what I can do is simply going to show it in the axis. So you're creating here the axis for the subplot of the 5 into 2. I mean, you have the 5 row and 2 columns. Cool. So in the first column, I mean the first columns, we're simply going to showing here the ultrasound images, I mean the real images. And the second column, for the subplot, you're going to show here the expert marks, I mean left side and the right sides. So you can see I am show and passing here the image, I mean this image, and in this case we're simply going to show here the marks. And make sure you give it here C map as a grayscale, because marks is nothing but on grayscale itself. Obviously you convert it in grayscale, but it's a better choice to showing here in a matplotlib. So you give it a set title, you give it a set title and the image files and the random index that we see on here, the same things. And then you give it here access equal to off, and you give it here title award and the plt dot show. Now you can simply go to using here shift and enter. So it will try to generating here some kind of images that you can see ultrasound images, and you can see marks, you can see marks, and you can see marks. Okay, that's it. That's it. Now you can see that how can we visualize the images from our data sets. Now you're going to checking here the image file and the marks file. It ends with the .png. I mean for checking purposes. So for f in os.listed, make sure that all of the images should be in the form of .png. Let's say in our data set we having one images containing here .jpg. So it may be giving here some kind of error problems. So that's why checking here if all the files is and with .png, which is a good quality picture, to passing here the deep learning. Make sure when you are actually creating here any kind of classification projects in the case of images, make sure you are using here .png files. It's a good choice. Then if f dot ends with the .png, then you're going to creating here a directory list. Inside the list comprehension, so you have the image file and the marks file. That's it. Now after that, you're also checking there is there any missing marks file or not. We already know that you don't have any missing marks file. If you have, then how can you checking them? So missing marks is equal to f for f in image file, if f not in marks file. If the f is not in marks file, that's mean if some of the data or some of the images is not available inside this marks file, it will give you one value error, missing marks, length of the missing marks, images including these ones. Okay, and then you're going to creating here a file pairs for the image directory and the marks directory. See, we're going to creating here a file pair. See, file pair means we are having the image file name, image directory, and the marks directory in a pair. Okay, in a pair, you can see os.path.join image directory passing here the app, because we're taking here all of the image file name and the marks file name. Now why we are going to taking it out? Because see, if I see the images, just to wait, okay, if I see these images, you can see you have the name also. See, this name and this name is completely same. See, this ultrasound name and this name, see, this is the file name, completely same. That's why checking for that. Let's say we having one mismatch name. Let's say this is nothing but the 1050 and this is 1049. That's mean one file is missing and one file is mismatch. So that's why checking it here. Okay, we need to checking it here. So we need to have one file pair so that we can also easily passing to inside our models. That's why. Okay, so you can see image file and the marks file. That's why checking that for a dot and png. So if it is the equal, that's been good, fine. But if it is not present, if the marks file is not present, that's when you give it here one missing marks error. And then you're going to creating here a file pair of the image file, because image files is nothing but giving here the same file name as the marks file name. समझिए आपको आप देखा तो आप अगेन बताता हूं मैं एक्चुअली देखो यहाँ पर जो रियल इमेज का फाइल नेम है ना, वो मार्क्स इमेज का फाइल नेम सेम टू सेम है. तो यहाँ पर थोड़ा मिसमैच हो सकता है, क्योंकि ह्यूमन तो हो सकता है ना, डेटा से जो क्रिएट किया वो तो ह्यूमन ही है, तो इसमें प्रॉब्लम हो सकता है. इसलिए तो देखो इमेज फाइल नेम और मार्क्स फाइल नेम तो सेम ही है. तो हम लोग क्या करते हैं, फर्स्ट चेक करते हैं यहाँ पे कोई मार्क्स मिसिंग तो नहीं है. मार्क्स मिसिंग हो तो प्रॉब्लम होगा, क्योंकि यूनिट का काम ही है सेगमेंटेशन करना. तो इसलिए हमने चेक किया मिसिंग मार्क्स को चेक किया. इसके बाद हमने एक पेयर क्रिएट किया. देखो इमेज फाइल एवं मार्क्स फाइल तो सेम ही है, इसलिए हम एक पेयर क्रिएट किया सो दैट यू कैन पासिंग इट इनसाइड द न्यूरल नेटवर्क मॉडल, आई मीन यूनिट आर्किटेक्चर्स. ओके, आप समझिए आपको. ओके, नाउ यू कैन यूजिंग हियर शिफ्ट एंटर, देन यू कैन सी दैट द डेटा फ्रेम. ओके, आप देखो डेटा फ्रेम सेम थिंग है. ओके, यू कैन सी इमेज पाथ एंड द मार्क्स पाथ. ओके, cool. Now what I can do, it also starting here on subject ID. So subject ID क्या है यहाँ पर? What is the subject ID? See, after this value, you're having one name called bass. See, we having a name called bass. Okay, this is the called a subject ID. Okay, so how can you start it? See, start subject ID from file name like. So let's say this is our file name, and this is our file name, and this is another file name. Okay, see, bas, and this is the vascular slice. So how can you do that? First, you're going to split it based on uh, this underscore, and then you're checking that if the length of the part is less than 3. Okay, if the length of the part is less than 3, I mean this is less than 3, so we give it here on error unexpected file format. See, unexpected file format, that's mean this file format is not correct because it have up to 4. See, bas and vascular, it's up to 4. Okay, maybe 4 and up to 4. So first part is nothing but part of 0, I mean this part, and second timestamp length we give it here at 80. I just give it some kind of timestamp, and if the length of the first part, I mean first part, is less than timestamp length, I mean how many length it have, just you're going to calculate it, and otherwise it will also give it here some kind of errors. Then you have the identifier, the first part of the timestamp length to up to them, and then we have the subject ID, identifier the split of 0 dot split, I mean the first one. So it's better you can running this out, then you can understand. So I can give it here one shell as well, and then I'm simply going to, okay, we having these ones. Okay, so let's run it. So you can see subject ID is nothing but called bas, and another one is called the em. This is the subject ID, I mean we're taking here the first, this one bas, and here is also bas. So 3, and we have the 3, okay, sorry, 3, then we have the 3, that's been 6, and we have the 9, see 9, and you have the 3, and we have the 3, and you have the 3, that's when you have the 18. That's why I give it here time stamp length as a 18, that you can see. So this is the full part after this underscores, it maybe happens. So because we have the 2 types of file name, that's why. So just taking here this bas, not taking the rest of them. Bas and vascular is the almost same name. So that's why checking here it have the any first path length or not. And then you give it here the identifier, and based on this identifier, we're going to give it here all of them. Okay, that's it. So you have the subject ID. This is for the bas and the EMs. Now it's time to creating here our UNET architecture. It's not needed at all, but just for simplicity or just for showing, you can use it. Okay, so now we're creating here our UNET architectures. So what I can do in our images, we simply going to convert the images into 256 into 3. First, let's have a look at the architectures. I actually found it in Google. So let's see the architectures of the UNET. I just searched on Google and founding these ones, which one is similar to this code. So you can see 60 into 60, and see 32 32, 64 64, 128 128, and 256 256. But here they're actually using here 128 cross 128 cross 1 images. But in our cases, we're actually using here the 256 and 256 into 3. Okay, but you can see the filter size is almost same. So in here you can see it will try to doubling it out. You can see doubling it out, 32 32, 64 64, 128 128, and 256 256. If you need one clear explanations, you can just go on my YouTube channel and follow here how can I code an UNET architecture from scratch. See, it have the count of 3 cross 3 with ReLU, max pool of 2 cross 2, up sample of 2 cross 2, important, see, up sample of 2 cross 2, copy and concat. See, it's called copy and concat, and this is count of 3 comma 1. This is the last one. Okay, for the segmentation tags. Okay, I just found it in Google. You can see more architectures, but image size is not correct at all. In our projects, you can see it using here 128 128, but you can see the filter size is nothing but 32. Sorry, kernel size is 32. Okay, so now what I can do is simply going to go on here. So see 16, 16 and 3 cross 3 is nothing but a convolution layer. So if I going to go on here, and if I see these architectures, so 3 cross 3 and ReLU. So 3 cross 3 ReLU, and padding make it same, and we passing here this input. So you're going to creating here inputs. So inputs and input size, and you're going to give it here. So this is the C1 and this is the C1. See, this is not an sequential model. This is on functional model. See, functional model. That's mean you have to passing here this layer to this layer. If I see this, you can see this layer is going to pass it from here. You can see if I zoom it out a little bit, it will be better. Okay, it cannot be, I cannot be zoom out, zoom in. So you can see it's nothing but this block sign is nothing but the max pool 2D, and also data is passing from this layer to this layer, you can see. So if I go on here, you can 16 and this is the 16. Okay, I think I need to closing the Kagolon, it's not needed at all. So then go on the full screen mode. See 16 and 16 with the convolution of 3 cross 3. See 16 and passing this input, and again it is passing to the C1 as a 16 cross 16. That's mean this one, this blue one. Okay, it is not blue, is the what is called, Mm, the beguni color. I don't know what it's called. Purple. Okay, purple. This color to this color, you can see. Okay. So and after that you have on max pooling. See, after that you have on max pooling. So you can say max pool 2 into 2. Then after that you have 32. So see 32. This one 32. So you can see 32. And same P1. P1 is coming from here. See, after max pooling, this is coming from here. Okay, so P1, and after that it's go to the C2, come to the 32 3 cross 3 activation ReLU padding same and C2. That's mean this data is coming from this image is coming from this layer to this layer again here, and this layer to this layer. Okay, like that. So from first it will just going to passing here this input images to this 16. So you see input image to the 16. Okay, and after that this output going to passing to the next one. So this output C1 is going to passing here the next one of the 16. And then you're having one max pooling layer that you can see. We're having one max pooling layer, max pooling layer. And now after this max pooling layer, it is going to the input of the next one for the 32. So see the max pooling one, this max pooling one going to the input of the next one for the 32. Okay. So again, it is going to passing it here, and then you can see it's passing to here as a next one. Same thing for max pooling 2D, and same thing for the same layer, next layer. 64 again, 64 again, you can see 64 again, and you can see 64 again, max pooling, max pooling, max pooling. Okay, and after the final layer, you can see after the final layer for the 256, it will go to passing it here, and after that it will try to do the up sampling. You can see try to do the up sampling. You can see up sampling. Okay, that you can see up sampling. So after 256, it will do the up sampling. So in here you can see it's try to the green sign. You can say up sample 2 cross 2. So first it will do the up sampling. So it do the up sampling up U7C. Make sure your name should be correct. The C6 is going to passing to, sorry, C5 is going to passing to inside the up sampling 2D. The C5, I mean this one. Okay, C5 going to passing to the U6. Okay, U6. So you can see up sampling 2D 2 cross 2, because we have, see, you can see 2 cross 2, and going to passing it inside the C5. And after that, you have to do the concatenations. You can see it is called the concatenation path. Concatenation. This is called the concatenations. So you have to do the concatenation in here. Okay. So you can see concatenation of the U6 and the C4. So U6 nothing but this one. So U6 is nothing but this one. And U and C4. This is the C4. I mean 128, 128. See 128, 128. You can see 128, 128. That you can see. Okay. You can see this is the C4. And this is the U6 that you can see. This is those are concatenate. You can 6 cross 16 cross 128 that you can see. Okay. And after that, what we have the next one. So next one is same thing, C6 and U7 and C3. If I go that, you can see here, this is the U7, this is the U7, and this is the C3. 1, 2, 3. This is the U3. See, it will also do the concatenate U7 and U3, and you have the 64 and 64. That you can see 64, 64. Same thing, you can see 64. That you can see 64. Okay, I hope so you see it. You can see 64. Same thing on here. You can see here U8 and C2. U8 and C2. So this is the U8 and this is the C2. You can see this is the C2 block. And which one is nothing but the 32. Okay, you can see 32. Same thing, you can 32, 32. Same thing, 32 and 32. That you can see 32 and 32. And again here is 16 and 16. Same thing, you can see here. This is the final one. 16 and 16. You can see 16 and 16. So you can see C9 and C9. Okay. Same thing passing here U9 and C9. And we need to concatenate here the U9 and the C1. So you can see U9, this is U9, and this is the C1. This is how you can do it out. You can also either using here the upsampling to the other, you can also using here the COM to the transports. And after that, we have the output. So because we have just one class, so it's the output, and we just have been passing it here one layer. You can say con 1 cross 1. Say con 1 cross 1. So that's when you can see 1 cross 1, and you need to give it here the how many classes you have. Then activation is sigmoid because you have the one class, and you passing here the C9, the last one, and you're going to creating here the model. Inputs is inputs and output its outputs, and then that's one model. That's one model. Simple as it is. Okay, and after that, to creating here a function for loading the data. So here you're going to passing here our data frame, and also you're going to passing here our image size. So you're creating here two lists for that. One is for the images, another one is for the marks. So we can easily accessing here the image path and the marks path from the data frame, because we already save it in our data frame. You can see in our data frame we already save it out, so you can directly access the image path and the marks path by using the iteration tactic. So you can see for image path and marks path in Jeep, and you give it here the df.image path and df.marks path. थोड़ा पानी पी लेते हैं. And after that, we are going to using the load image that you already imported. The image, load image, and image to array. So we load it, the image path and target size, we pass it here to the image size, so that it will automatically resize the images to the 256 and 256. And then to convert this image into NumPy array, or you can say array, image to array, and it also divide by 255. Why? So because you need to also do the normalizations. So how can you normalize them? We can normalize them by dividing the maximum number of pixel value. So in the one images, the minimum value is 0 and maximum value is 255. So that's why dividing them, now the data range should be between the 0 and 1. And then you append it to the images. Same thing for the marks. Okay, I'm not going to explain it because same thing for the marks. And after that, you convert them into the NumPy array. np.array of the images and np.array of the marks. See, and then you're going to using here this functions called load data, and you give it here the df, but you're not going to passing it here the image size 256 on here because it's by default. I'm going to give it here. Okay, default parameters. And then marks is equal to np.expand dimension of marks axis is equal to 1. Now why this one? Why? We simply going to reshaping them. We reshaping them with the number of images, okay, number of images, or how many images you're going to passing it here, with height and number of channels. Okay, I mean number of channel, how many that. This is called the expand dimension. It's nothing but for the reshaping. So you give it to then all of them, and we're going to create shaping them so that you can passing to inside the CNN model, because it's nothing but an CNN model itself, the UNET architectures. That's why. And now shift enter, and now it divide our data set into training and splitting. I mean training, test, and splitting, that you can see. So I passing here the images and the marks, and test height is 0.2, and random state, you give it here 42. So you have the x train, x test, y train, and y test. So using these one, we can also calculate here the dice and as well as the IO. Okay, I mean the evaluations for the evaluations. And now we can simply go into installing here something thing just called graphics beach, and also installing the graphics and PyDot, so that you can also show our models, okay, in kind of plot. So we are calling it here model is equal to UNET. We're calling this out, and now using this TensorFlow.keras.utils import plot model, we can simply go to plotting here our architectures. So shift enter. So it will try to creating here this UNET architectures, and I am simply going to plotting this out, that you can see. Okay, so you can see how your model look like. So you can see. So if I download this out, let's say save image, as this one, I already downloaded this out. So you can also see one more thing if I go back. So this is the image that you can see I downloaded it. So if I going to flip it, you can see it's look like EU. You can see it's look like EU. That's what it's called, the UNET, that you can see. Okay, look like the EU. You have all of the things you can see. Okay, that's it. Now what I can do is simply going to training out our models. Okay, so let's go down, and now let's see. So we are using here model.compile. First, when you are trying to training any kind of models, you need to also compile your models. So model.compile and optimize the gives Adam, and loss is binary cross scientific because it's the binary classification types of tasks. Matrix is accuracy, and you also give it here the earliest stopping. Earliest stopping is equal to patience after tens. If the validation loss or accuracy is not improved, or loss is decreases, you simply going to stop it out. So you have the verbose is equal to 1, so that you can also show the process, and restore best word is equal to true, and reduce LR equal to reduce LR on plateau, so that you can also see whether the learning rate should be increases or not. Okay, I mean just give it some kind of patterns. And then you give it here history is equal to model at feet. You're passing here x train and y train and validation data. You're passing here x test, y test, epoch is 5, pass is 32, callbacks give it to here. And you also calculate here the loss and accuracy after evaluating our models. Now what I can do, I am simply going to shift enter in order to running this out. And I'll back again when the training is completed, because it's time consuming. It's almost taking here the 1 hours to training this out. And after that you're going to do the plotting, and then you're going to calculate the IOU and the dice and do the predictions, as well as we are going to save the models and also going to checking it for the real-time images. Okay, so let's wait for 1 hour, and after 1 hour I'll back again, because obviously taking time. So our training is complete, but it's taking just less amount of time. I don't know why it's taking so much of time tomorrow while I'm actually running this code. Or maybe I just set the runtime in the form of CPU. Maybe that's a problem. But in the case of GPU, just taking here 2 or 3 minutes. Okay. So after that, we got in here 98% accuracy, and validation accuracy is 99%, which best result, I think. Okay. So accuracy 99% and loss is 0.0171, and test accuracy is 0.9934. Cool. Now we need to also do the plotting. So for that, you're going to be creating here a function called plot history, which I'm taking here and history itself. So history is nothing but coming from here. It's nothing but the variable that you created. So first you're going to creating here figure. So PL figure of fixed size of 12,5, and creating a subplot of 1, 2, 1, so that you can also show the training and the loss as well. So plt.history.history.accuracy, from the history.history.accuracy, you're taking here the accuracy. And if validation accuracy in the history.history, we're plotting here the validation accuracy in the upper left case, in the upper left. Otherwise, we're just showing here the model accuracy. And in the subplot number 2, we're just showing here upper left part, the training and the validations loss. You can see the loss. So this is nothing but for the accuracy, and this is nothing but for the loss. Okay. And otherwise, we're simply going to showing here the model loss and have the title award. So I'm not going to explain it out because it's simple. So shift enter, and you can see the accuracy. So model accuracy is increases and loss is decreases, that you can see. Now it also calculate here the IOU. So how can you do that? You can using here this np.logical and you can give it here the logical and you can pass it here the y true and the y predictions and taking the sum, so that you can show the intersection union options in the case of UNET architectures. So intersection is nothing but how can you calculate them, intersections, and how can you calculate the unions. So logical OR is nothing but y true and y predictions and taking the sums, and if the union is equal to 0, just returning here 0, otherwise we're returning here the intersection divided by unions. And now how can you calculate the dice? Simply you need to also calculate the intersection first, and after that you can do the total of the true and the predictions. So this is how can you calculate the dice. So you can see this one, and then you can simply returning here 2 into intersections divided by total number. Okay. So shift enter. And after that is simply going to do the predictions using the X test data, because we have so testing data. So if it is up to 0.5, we're taking here the predictions. So up to 0.5, and as type is nothing but the Boolean format. And then you have the test binary. So we test.s type is equal to bool. We're simply going to convert them into the bool. Okay. And after that, we're simply going to calculate here the IO and the dice. So you're calling here the functions called calculate IO, and you give it here the y test binary in the from sequence and y test binary in the from sequence. And same thing for the dice. You can see y test binary and y test sequence. This is nothing but for the change in the shape of our data frame. I mean, change the shape of our matrices. And now you can simply go to printing here the IOU and the dice. Okay, you can see it will do the predictions, and this is the IOU 73% and dice is 84%. You can also see the model summary as well, so you can see the how the model summary look like. So you can see starting from the 256, 256, 256, 128, 128, 64, 64, 32, 32, 64, 60, 60, 60, and again it will increase 60, 60, 32, 32, and 64, 64, 128, 256, 256, like that. Okay. How many parameters, how many trivial parameter and non-trivial parameters, and optimize the parameters. You can also saving here the model, so you can simply go into using here this model.save, and you can using here the model.keras. So you can also download it and you can also use it later on. Now you're going to checking that how can we testing this out. So for this case, you import here the numpy cb2 matplotlib, and also one more thing, TensorFlow.keras.preprocessing.image load image and image to array. Then you also give it here on real image path. You need to also give it here on email image path. You have to getting here the mux image path. And after that, you're going to creating here a function which is called a pre-process single images, because you're going to give it here the single images. So image path target size is 256, 256. So we load the images using this load image, this the load image. And after that, you give it here the image path, and the target size is that is passing from the default parameters. And we also convert them into the normalize. I mean, we numpy array, and we also normalize it, and also do the expand dimension, to give it the best dimensions. I mean, so that you can also reshape it. In the case of batch, how many batch of the image it coming up, and width, height, and the number of channels. Then you're going to creating here test function for checking here the real images. So test the real images. We calling here this process the single images, and then you also do the predictions. So model dot predict, and you give it to the input images, and you get the 2D prediction of that, and load the original images for display. So you can using here cbt.cbt color, and you can passing it here. I am read the image path. I mean the image path that you actually getting it from here, the image path, and cbt.cbt color bgr to rgb. So this is nothing but for the load the original images, and then you're going to plotting here the predicted marks by our models. So for that, you're going to creating here and pl.figure, you're creating figure size, and you're also creating here a subplot for the real input image, and another one is for the mux images that you can see passing here the image show. So this is the image show, and then the prediction was nothing but coming on here the predictions. So getting here the prediction inside that. So if the prediction is greater than 0.5, then you are going to show the binary marks, and you also give it here cmap as a grayscale. And then PLD title is predicted marks, and axis off, and title out. And then you're calling here the functions called test real images, and then you're going to passing here our real image path. That's it, you can see. So you can go on here, and you can copy here any kind of real image path. So I can reload it, and then I can also taking here one images from these data sets. Okay, so I going to go on here, export mux images, and these are mux images, and I'm going to taking here one us images, I mean the real images. So let's taking any kind of random image, copy path, and then I'm going to give it to here. Let's going to give it to here. Okay, I can give it to here like that. Okay, so let's delete it first, and then I am going to give it to here the path. Okay, that is copied. Now shift enter, and let's wait for the output. So you can see it's the output. I hope so. You can see the real input images, and this is the predicted marks that you can see. Okay, this is the real input image, and this is the predicted marks. Cool. Okay, that you can see. So this is how the full applications, I mean full code actually work. Real image and the predicted marks. You can also creating here and applications using Flux or Streamlit or the Gradio library. So it's your homework to do that. So that's it for today now. I hope you enjoyed this full tutorial, and make sure to subscribe our channels, and don't forget to hit the bell icon so that you can notify when the new videos uploaded to our channels.